All right, we're talking about counting, and so there are going to be different ways of counting, and so I want to talk about permutations, combinations, and arrangements. So I'm going to talk a little bit about that first. Let me just add a page here right now. So I added a page, and so we learned. So what's going to happen is let me talk about arrangements first, right? And then they're going to be permutations, and then they're going to be combinations. Okay. All right, so let's just suppose we had the numbers, a combination where you had 6 numbers and you have to arrange them in 6 spaces. So let's suppose it's 1, 2, 3, 4, 5, and 6, and you have to arrange them in the spaces 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we'll leave combinations out for just one moment, right? And so now the question is, how many ways can you arrange these 6 numbers right here? And I guess I should make them letters. So let's do A, B, C, D, E, F, right? Okay, so I could arrange them in all sorts of ways. But the question is, can I repeat letters? If I can repeat letters, then we're talking about an arrangement with repetition, in which case I can do A, right? And then that counts, or B, 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 and so forth, right? So in that case, I have 6 choices here, 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 and 6 choices here. And therefore, the answer is 6 to the 6th power, because you multiply. We learned that last time. If you don't repeat, so if there's no repetition, then you have 6 choices for the first one, then 5 choices for the second one, 4 choices for the third one, 3 choices for the second one, 2 choices for the 5th one, and 1 choice for the last one. And so this is 6 times 5 times 4 times 3 times 2 times 1, right? Now this comes up so often, 6 times 5 times 4, when we're counting, that we actually give this a name. It's called 6 factorial, right? So 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And so whenever you see this exclamation point next to a number, you're just going to take the number and multiply times all the integers less than it, all the way down to 1. We'll get the combinations in a second. Now, the difference between permutations and combinations happens when I have, let's say for instance, I have 4 people, Anthony, Bob, Christina, and Diana, right? And now I need to select, there are 4 people. I need to select 2 people to do something. All right. And so let's see what those 2 things are. I need 2 people to go to the store. Over here, I need 2 people. One will be the president, and one is going to be the vice president. And so now I want to count how many ways I can do this, right? And so here, what's the difference between these? I'm going to get different numbers. And so let's see why. So let's count over here. 2 people go to the store. Well, A, B could go to the store. AC could go to the store. A and B could go to the store. A and C could go to the store. A and D could go to the store. What else? B and C could go to the store. B and D could go to the store. And C and D could go to the store, right? So there's 6 ways that I could take 2 people to just go to the store. Okay. Over here, though, it's slightly different because here A could be president and B could be vice president. B could be president or A could be vice president. You see the difference? A could be president and C could be vice president, or reversed. A could be president and D could be vice president, or reversed. And so forth. So B could be president, C could be vice president, C could be president, D could be vice president, B could be president, D could be vice president, D could be president, or B could be vice president, or C could be president and D could be vice president, or D could be president and Z could be vice president. So this now is 12 ways and that is 6 ways. So what's the difference in these 2 ways? Well, this one, it didn't matter. I just needed to pick 2 people. Right? I need to pick 2 people. Here, order does not matter. That is called a combination. And here's the formula. It's going to be 4 factorial, that factorial thing I just talked about, all over 4 minus 2 factorial. And in general, it's in fact, if you want to take n, if you have n things, you need to pick r of them. This is times 2 factorial. Then it's going to be r factorial times n minus r factorial. When order does not matter, you use this formula. We'll be practicing this a lot. When order does matter, and you care AB is actually different from BA, then you're going to get more than you would when you did a combination. And it's called a permutation. By the way, this over here is called the choose, right? So I might say 4 choose 2. So for instance, this is 4 choose 2, and that is how we're going to type it into Google when we want to calculate something. So for permutations, here the formula is 4 factorial over 4 minus 2 factorial. Right? And in general, it's n factorial over n minus r factorial. When you have n things, you want to pick r, then you have to decide whether you care about order or whether you don't. If order doesn't matter, then you're choosing this one, no pun intended. If order does matter, then you're doing permutations. All right. Let's get to the exercises. What are arrangements with repetition? Give an example of a situation in which n to the r formula gives the number of possible arrangements. Number 1. So when they're just arrangements with repetition, you can repeat. You're just going to be multiplying n times n times n times n, like we did with the 6's earlier. Give an example of a situation in which the n to the r formula gives the number of possible arrangements. Suppose that a license plate has 6 numerals, 1, 2, 3, 4, 5, 6. And how many different 6-number license plates are possible? So you can have 0 through 9 and nothing stops you from repeating. So I could have that, right? So that means that there's 6 choices for the first one, 6 choices for the second one, 6 times 6 times 6 times 6, right? I'm sorry, it's not 6. It is 10 choices, 10 times 10 times 10 times 10 times 10 times 10. That is 10 to the 6, which is 1,000,000. So it's A. Decide whether the following statement makes sense or is clearly true, or does not make sense or is clearly false. Explain your reasoning. Linda uses permutation formula to determine how many possible relay orders could be made with the 10 girls on the swim team. So she has 10 girls on the swim team, and she's trying to order them, right? So the question is she going to use combinations or permutations? And so the real question is, does she care about the order, right? And she clearly wants to order them, okay? So the statement makes sense because she cares about the order. We said earlier that for permutations, you care about the order. Right? You care about the order of permutations. And so, yes, she would be using the permutation formula for this one. This statement makes sense because all selections come from the same swim team. Each girl can be ordered only once and can be selected only once, and the order matters. We care about the order. My number two is C. Number 3, determine whether the following statement makes sense or is clearly true or does not make sense or is clearly false. The number of different possible batting orders for 9 players on the 25-person baseball team is so large there's no hope of trying them all out. It's a ton, right? So that is going to be B. Let's see why that is. So now we, again, just like the swim team, we care about the order. So it's 25 and it's permutations P9. And this is actually on the TI-84 calculator. So you can actually calculate these and just put in 25P9. Let's see, but if not, you can just go, it's on Google. 25 people. You need to pick 9. You care about the order, and so it's a permutation. Let's calculate. That is over 700 million. 700. Wait, that's 700 billion combinations. 1 million seconds is 11 days, so 700 billion seconds is much, much longer than that. It would just take too long. 700 billion batting orders. Decide whether the following statement makes sense or is clearly true or does not make sense or is clearly false. Explain your reasoning. The probability that 2 people in a randomly selected group will have the same last name is much higher than the probability that someone in this group will have the same last name as you do, right? So if I go into a group of people and I ask, I'm looking for the probability that any of those people have the same last name as me, versus going and just selecting any 2 people and seeing whether they have the same last name, that is much more likely the second one, right? So the statement makes sense because the coincidence of any 2 people having the same last name is higher than just me, right? I'm actually just a subset, right? So me having the same last name as anybody has a less probability that any 2 people in the room have the same last name, because there's more of them than me. So it's much more likely that that happens for them. That was number 4. Number 5, we're going to do this calculation. Actually, this was the one we had before. 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Again, we are going to, when we're counting, that happens so often that we actually have a name for it. 8, and the factorial button's here actually. So 40,320. 14 factorial over 10 factorial. So 14 factorial, I'll calculate 14 factorial divided by 10 factorial equals 20,024. I'm sorry, 24,024, right? 24,024. Let's see if we can do this one. 13 factorial divided by 11 factorial, and then divide that by 2 factorial equals 78. Calculator. Similar thing here, 14 factorial all over 4 factorial, and then 14 minus 4 is 10, so this is just 10 factorial. We'll do that. So then 14 factorial divided by 10 factorial equals, and then divided by 4 factorial equals 1001. Same thing here. This is just 15 factorial over 3 factorial, and then 15 minus 3 is 12 factorial. Calculator. 15 factorial, it's a huge number, divided by 12 factorial equals that, and then I need to divide by 3 factorial. It's 455. Let's zoom out a little bit. How would we do this? Answer the following question using appropriate counting technique, which may be either arrangements with repetitions, permutations, or combinations. Be sure to explain why this counting technique applies to the problem. I got a 7-digit code, 1, 2, 3, 4, 5, 6, 7, and I can be used the digits from 0 to 9, and it looks like I can repeat. So this is definitely arrangements with repetitions. I can have repetitions with no problem, and so this is arrangements with repetition because there are selections from a group of n choices, right? So there are 10 choices, and I want to. So in this case, there are 10 choices, and there's 7-digit codes, right? And 7 selections. So that's going to be 1, 2, 3, 4, 5, 6, 7, and it's going to be 10, 10, 10, 10, 10, 10, 10. It's 10 to the 7th, which is 1 with 1, 2, 3, 4, 5, 6, 7. 1 with 7 zeros. 10 million possibilities. So that one is D. Answer the following question using arrangements with repetition, permutations, or combinations. Be sure to explain why the particular counting technique applies to the problem. How many 6-character passwords can be formed from the uppercase letters A through F if repetition is not allowed? All right, I'm not allowed to repeat. A through F, A, B, C, D, E, and F. Good, that's 6. So I got 1, 2, 3, 4, 5, 6. And it looks like I'm going to, and actually this is 6-character passwords, so I actually do care about the order. So I care about the order, right? And because I couldn't repeat, it wasn't what we did last time. So that means it's either, so it wasn't arrangements with repetition because I couldn't repeat. So it's either permutations or combinations, and that now depends upon whether I care about the order. And when I'm doing the password, obviously the order matters, and so this is just a permutation. And so you could do 6p6, or you, and just put that in here. Let's see what we get. 6p6. There's 6 items to choose from, and I have to put all 6 of them down. 6p6 is 720. That's the answer. And here's another way to get it. There's 6 choices, 6 letters I could put here, 5 letters I could put here, 4 letters I would put down, then 3, then 2, then 1, and you would just multiply. Either way, it's 720. Permutation should be used because no item may be selected more than once, and I care about the order. 720. A DJ is preparing a playlist of 17 songs. How many different ways can the DJ arrange the first 6 songs? So there's 1, 2, 3, 4, 5, 6. Again, you can get this in a couple of different ways. Here, of course, I want to arrange the first 6 songs. I care about the order. That's 17p6. We can go ahead and put that here, right? 17p6. That's 8,910,720. Again, I think the other way to get it, of course, is that there's 17 songs to choose here, and 16, then 15, then 14, then 13, and then 12. Let's see if that gets you the same thing. Right, so then 17 times 16 times 15 times 14 times 13 times 12 gets you the same thing. Answer the following question using the appropriate counting technique. How many possible birth orders with respect to gender are possible in a family of 4 children? They better tell us about the order. They're saying that these are different orders. Okay. So you've got 1, 2, 3, 4. And it looks like you can definitely repeat with the B's and G's. So the 2 choices here, 2 choices here, 2 choices here, 2 choices here. You can repeat. So it's definitely arrangements with repetition because you can repeat. And you just go ahead and multiply. So 2 times 2 times 2 times 2 is 16. Answer the following question using the appropriate counting technique. Let's see what we got here. How many license plates can be made of the form XXY? So 2, 3, XXYY, right? Where X is a letter of the alphabet and Y is from 0 to 9. Looks like, again, they can repeat. And so we're going to be doing arrangements with repetitions, and you can repeat. How many are there? So there are 26 here, 26 here, 26 here, letters in the alphabet. And the last 2 are digits 0 through 9, which is 10, 10. So it's 26 times 26 times 26 times 10 times 10. 1,757,600. Yeah, oh great, they gave us that choice. Answer the following question using the appropriate technique. All right, so I've got how many different telephone numbers? Here we go. So I've got AAA, BBB, CCC. AAA can't have the number 1, and BBB can't have the number 6. 2, 3, 4, right? So this first group can't have the number 1. So normally I would have 10 choices, but I only have 9. By the way, this is definitely arrangements with repetition, right? So choices can be repeated. So, but I only have 9 choices for these first 3 because they said I can't have the number 1. And I only have 9 choices for the second 3 because I can't have the number 6 in any of them for whatever reason. And then I have 10 choices for the rest of them, right? So I just need to figure out what that number is. And that number is going to be huge. I don't know if that number is going to be able to be put in this calculator. 9 times 9 times 9 times 9. As a matter of fact, let me just do 9 to the 6. So 9 raised to the 6th power. Right, and then times, and then I just need to add 4 zeros on that, times 10 times 10 times 10 times 10. That obscene number. And then I would just put that number in. Oh, that number's here. They gave it to us. Sweet. Answer the following question using arrangements with repetition, permutations, or combinations. How many rearrangements do you have of both or can you make? Well, so I just have to rearrange these letters. 1, 2, 3, 4, 5, 6. I believe it's 7 letters. And then I can just put these letters down however I want. Where there's 7 letters, I need them to put them in 7 places. So again, that's just 7p7 because I actually do care about the order, right? So how I put these down, I will count as a particular arrangement of the letters. And so that's 7p7, or again, that's 7 letters I could put in the first place, which would leave me with 6 to put in the second place, 5 to put in the third place, and so forth. 7 times 6 times 5 times 4 times 3 times 2 times 1. That is 7 factorial actually. So I can just put that in the calculator. 7 factorial is 5,040. An ice cream shop offers 25 different flavors of ice cream and 11 different toppings. Answer questions A through D using the appropriate counting technique. How many different sundaes can you create using 1 ice cream flavor and 1 topping? Whether there are 25 ice cream flavors, 11 toppings. Wait, give me 1 second. I'm gonna need to charge my laptop. So 25 choices for the flavors, 11 choices for the toppings. And so there you just multiply 25 times 11. $275. Here you're just doing the multiplication principle, right? How many different triple cones can you create from 25 flavors if the same flavor may be used more than once? So it sounds like you're repeating, right? So that's definitely arrangements with repetition. And for the first scoop, I have 25 choices. If I can repeat, I have 25 choices for the second scoop. And for the third scoop, I still have 25 choices. So it's 25 times 25 times 25. That's 25 to the third power, 15,625. Using the 25 flavors, how many different triple cones can you create with 3 different flavors if you specify which flavor goes in the bottom, the middle, the top? Sounds like the order matters now, right? So this is 25P3, which you can put in your calculator, or it is 25 times 24 times 23. 13,800. Using 25 flavors, how many, oh, by the way, this is definitely permutations because you care about the order. The order matters. Using the 25 flavors, how many different triple cones can you create with 3 different flavors if you don't care about the order? Right, so that is now combinations. So that's 25C3, or if you want to put this into Google, it's called 25 choose 3, right? And so we call it choose because it's 25. You get to choose any 3 where you just don't care about the order. So that just goes right into Google if you want 25 flavors. We're going to choose 3 of them. 2,300. So that's combinations. Because the selection comes from a single group of items and the order does not matter. We don't care which order they come in, so you just take any 3. Find the probability of the given event. Choosing 7 numbers that match 7 randomly selected balls when the balls are numbered 1 through 34, 1, 2, 3, 4, 5, 6, 7. All right, here they're not going to go back in for the lottery, so it's 34 times 33 times 32 times 31 times 30 times 29 times 28. Or we can just go ahead and use the P calculator that this is 34P7. Either way, you're going to get the same number. I think I'm going to go the internet route, 34P7. Again, on your calculator, you'll be able to do this. 34P7 is... Oh, actually, I don't care about the order. It's C. Yeah, I don't care about the order. When you win the lottery, you don't care about the order in which it goes in. So it's choose. It's 34 choose 7. It's that. It's 1 out of 5,379,617. 1 out of 5379 616. Right. So, and if you had done it this way, then you would have gotten it immediately. But just make sure we need to do 34C7 because I don't care how these numbers come out. The order does not matter when you're trying to win the lottery. Find the probability of guessing the top 2 winners from a group of 18 finalists in a spelling bee. The probability that someone correctly predicts the top 2 winners from a group of 18 finalists. Now the question is, do we care about the order? And it says in any order, so we don't. So it's 18, choose, we just need to pick 2. We don't care which order, I just need to pick the top 2. And I don't need to pick the order. So that, again, that's 18, choose 2. And that is 153. So the probability is 1 out of 153. A lottery game is played in many places and requires $1 per ticket to play. To win the jackpot, a person must correctly pick 4 unique numbers from 35. You don't care about the order, so it's 35. Choose. You got to pick 4. And we learned last time that and means multiply. correctly pick a final number, which is chosen from the balls numbered 1 through 25. So there are 25 of those numbers, right? So the total number of numbers you have is 35. Choose 4. That's the number of ways of getting 4 numbers from those 35, where you don't repeat and you don't care about the order that those 4 numbers come, and times 25 for each of those numbers that you pick separately. So we're just going to do that. 35 choose 4. Okay. And then I need to take that and multiply it times 25. And that is going to give me 1.309 million. 1,309,000. Hope it helps.